So our focus has subtly changed with power series from, given a function, what is the power series representation? And we really hammered that in the previous section. So we're focusing now on, given a function, what is the power series representation for that function? And we got to this point through Taylor polynomials. So I want to give a formal definition for a Taylor series now. And we already have a general, hold on one second. Sorry about that. So let's get a formal definition for a Taylor series. And it looks just like your Taylor polynomials, except that it extends to infinity. So a Taylor series is just simply an extension of the Taylor polynomials. All right. Go out one more term here. And it continues on to infinity. So the summation for a Taylor series in summation formula goes from 0 to infinity. The kth derivative evaluated at a over the k factorial. Whoop, that's a mess. Times the polynomial term x minus a to the k. So that's the form for a Taylor series. And really it's just an extension of the Taylor polynomials. A special Taylor series is one that is centered about 0. And that is called a Maclaurin. He was a Scottish mathematician. So Maclaurin is simply a Taylor series with center of a equals 0. So it's a Taylor series centered at a equals 0. So if a is equal to 0, take the general Taylor series and evaluate it, and you'll get a formula that looks like this. Continuing on, and the summation for Maclaurin is this. So now we have a formal definition for a Taylor series and a Maclaurin series. For Taylor series to be useful, a couple things you need to know about them. So let me scroll here and write down. I'm going to pause. So there's 2 points of interest for Taylor series. And the first is what we've been working with, the interval of convergence. And that's really, just like the interval of convergence for the power series, it's the values of x for which the Taylor series converges. And the techniques from 9.2 is what we're going to drop back to for that. And the second point of interest is really values of x for which the Taylor series for f actually equals f. And this is a little bit more, it's tougher. We're going to look at this briefly. And this is a tougher area, but we'll look at it briefly, and then further mathematics you'll get exposed to more of this is theoretical, but it's a tougher nut to crack. All right, so we're going to use the table method to help organize our work, just like we did with power series. So we're going to use the table method, and I'd like to do an example, and then we'll pick up in class. So use the table method to help organize and build your Taylor series. Alright, so let me pause and get an example set up. Okay, the example that we're going to look at is the function 1 over 1 plus x squared, and you're asked to find the first 4 terms of a Maclaurin series. So as soon as you see the word Maclaurin, you know that a is equal to 0, or it's centered about 0. So I'm going to tell you that doing the table method can get rough with further derivatives. So use Maple. Okay, use Maple to help you out here. It's a lot easier. All right, so let's begin. So that's when n equals 0 is just the function, and evaluating it, and of course this is just 1 plus 0. Oops. Sorry about that. 1 plus 0 to the negative 1, which is just 1. So when n equals 1, you've got to take the first derivative, and that becomes minus 2x, 1 plus x squared to the negative 2. Evaluate it at 0, and you get 0. The third order is, again, the derivative of the second, right, which you see a product rule. So this, you can see this is starting to get nasty pretty quickly. 4x cubed, and I'm assuming you can all do the product rule by now. And looking at that, you get this. Evaluate it at 0, and I'm sorry, I skipped a second. That's not good. Hold on. Well, instead of rewriting it, let me just put the second here. Put a little arrow. That was the third order derivative. So the second order derivative is 8x squared. Second derivative, 1 plus x squared to the minus 3 minus 2, 1 plus x squared to the negative 2. Okay. Evaluate that at 0, and it comes out to negative 2. And then 3, you can see there's next term multiplying both of these, so you don't need to spend too much time to see that that's going to be 0. So let's pick up with 4, and I'm going to do just a couple more, and I'm going to tell you that after about here, I used Maple. I went out to the second derivative, and then I gave up, and that's why we have Maple, to do higher order derivatives for us so that we could build this table. They asked for the first 4 terms, and it's actually the first 4 non-zero, so non-zero terms. Okay, so continuing along in this vein, you've got a very labor-intensive effort to actually come up with the first 4 non-zero terms of the Maclaurin. But Maple certainly simplifies the job. So I'm going to tell you that I used Maple. I'm not going to write them all. When n is equal to 4, this is 24. And when n is equal to 5 and 6, you had 0 and negative 720. Okay? So, you know, these higher order derivatives got complicated, but using Maple will help. So hopefully you notice that the odd powers here are dropping out. So we have this series looking like, I don't remember what your Maclaurin is. Actually, it's 0, f of 0. Write it better than that, not a. F of 0, f prime of 0. So you're going to use the table to help you fill in the terms here. Etc., etc. On out. Okay, what this looks like is 1 minus x squared plus x to the 4th minus x to the 6th. So we have this dropping out of the odd powers. So let's write the summation, which is the second part of the problem. Write the summation, representation of the function 1 plus x squared. And you notice that it's alternating, so you've got to put a alternating term in there, and then it's x squared to the k. Now there was an easier way to do this, and I'll point it out in a minute, but I wanted to take you through the process of finding the Maclaurin terms, and it's very similar to what we did in 9.2. And this is x to the 2k. So what you could have done is noticed that it looks like a geometric. Notice that it's a geometric. And it's a geometric for minus x squared. So this is 1 over 1 minus x squared. It's a lot easier. And you would have arrived at the same spot. Okay? You would have arrived at the same spot, which is a lot easier. The interval of convergence, but I wanted to walk you through the process. Okay, you could use the ratio test, or again you can use knowledge that this is a geometric and know that the absolute value of x squared has to be less than 1. So this is simply less than 1. Testing the endpoints, again you don't need to because it's a geometric, but if you went down the ratio test then you would test the endpoints. Just be consistent with your approach and your arguments to prove these things, and your interval of convergence is -1 to 1. Okay, so that's how a Maclaurin series works, and again it should look very similar to you, and a repeat for a good bit of the procedures that we did in 9.2.